Okay, well, the slope of this, what's your first thing you think of when you think of slope? You might think y2 minus y1 over x2 minus x1, but that's totally irrelevant, that's totally unnecessary here. The simplest thing to think of when you think of slope is rise divided by run. Then you don't need subscripts to do that, unless you've got subscripts in these things, okay? And if you have subscripts in these things and the variables don't match x and y, it gets confusing. And you can just think directly, rise divided by run, okay? So, it's very clear that we can complete a triangle there. I call that a fundamental triangle. It's a very important construct. This is rise. This is run. What is the run?
Y plus delta y minus y.
But what is that?
It's just delta y.
Yeah. And your answer is absolutely right. You're going to subtract this from this. But when you see a y and a y plus delta y, you know that the interval from here to here is delta y, right? So, and you should absolutely be able to check that by doing the subtraction. You got to know that.
Yeah.
Because it's a good answer. But we can just kind of cut through that once we understand how this works. So your run is delta y, and of course that's what you end up with down here, right?
Mm-hmm.
And that's a run. So we're just interpreting this expression in terms of the picture. Okay, the rise is what? Well, the rise is this y coordinate minus this one, right? Okay, so the slope is this, right? Which is just the average rate of change.
Yeah.
There's more, average rate of change of f of x, y, or z with respect to y, okay? On this interval. Okay. Now, as we let delta y approach 0, what happens to this line segment in comparison with this curve? So let me draw a little more grasp of curve. And let me draw a nice red slope, right? Okay? Well, the slope deviates from the curve. Okay, this segment isn't all that close to the curve. I mean, it's pretty close, the way I drew it. But if we shrink delta y down to here, the curve hasn't had much room to curve. It hasn't changed direction much. So what we can say is direction of the curve deviates from the direction of the segment. I could call that a chord, but I don't want to confuse the issue with a lot of terminology, okay? But I don't think it would distract you much if I called that a chord, okay? So for this one, okay? Much less deviation here, right? In other words, the slope of this thing is very close to any slope that you could get between these 2 points. Whereas here, you know, the slope could be, well, slope is lower here and higher here, right? So if I redraw the picture, with this chord, well, here the slope could be as low as this or as high as this, right? If I choose 2 points very close together, near this left end point, I get a slope something like this. If I choose 2 points very close together here, I get a slope that looks like this. Okay? So and of course, this corresponds to bigger delta y than this does, right? So as delta y approaches 0, you expect this slope to stabilize at some value, right? And that value, it turns out, is the slope of a tangent line at this point. Okay? Now that's something you learned in Calculus 1. Okay? Right?
Yeah.
But hopefully now that we've reinforced it, you understand it better than you did then.
Yeah.
Okay? Because it's something you really want to grasp. And some that's, you know, I really love the way this course ends with multivariable calculus, where we actually do first semester as well as second semester stuff. You know, we're doing derivatives and stuff. Second semester, we don't do much with derivatives.
Yeah.
So this kind of ties things together. So you'll see a lot of parallels, and a lot of things that you're going to understand better now than you did when you took your first semester calculus. Okay? Okay.